Okay, so we're going to prove that A intersection B union C is equal to A intersection B union A intersection C for any sets A, B, and C. So this is known as the distributive law of sets, and we're going to use the distributive law of propositions in order to prove this statement here. So let's go ahead and start the proof. So we're going to have X be an element of A intersection B union C. So by definition, this means that X is an element of A and X is an element of B union C. And then by definition again, we know that this implies that X is in A and X is in B or X is in C, right? So we can see that the statement is of the form P and Q or R, right? So we know the propositional logical equivalence of this statement here is going to be P and, so let me give some space, P and Q or P and R. Okay, so I know that P and Q or R is logically equivalent to P and Q or P and R. This is the distributive law of propositions. So what this is saying is, so we have, so P is X is A in A, and so Q is X is in B, or X is in A, and X is in C. So notice how I use the logical equivalence of P and Q or R to get to P and Q or P and R, where P was X is an element of A, Q is X is an element of B, and R is X is an element of C. So now we can go ahead and continue the proof. So by definition, this means that X is in A intersection B, right? Or X is in A intersection C, right? And then, of course, this by definition implies, or if and only if, right? X is an element of A intersection B union A intersection C. So we have X is an element of A intersection B union C. And by using definitions and logical equivalences, we're able to get that X is an element of A intersection B union A intersection C. So for every X, we have X is an element of A intersection B union C. If and only if X is an element of A intersection B union A intersection C. So since we have this statement here, that means we have that A intersection B union C is in fact equal to A intersection B union A intersection C. And that is the proof. Okay.